All right, today we're going to learn how to work with piecewise functions. And so it tells us up here that sometimes a function is defined using different equations on different parts of its domain. For example, an absolute value function is actually defined by two equations. F of x when its x is greater than or 0, and f of x equals negative x for x is less than 0. For convenience, these two equations are generally combined in one as this form of an equation. This is what a piecewise equation looks like. It tells us f of x, and then usually there's not this middle part. F of x is equal to the bracket and then the definition of the two. It's telling us that when x is greater than or equal to 0, we are going to use this equation. And when x is less than 0, we're going to use this equation. That is called a piecewise. When a function is defined by different equations on different parts of its domain, it is called a piecewise defined function. We're going to skip this first one because it's really hard to read that. I want to make sure you can see the equations here. So we're going to go to this one. And our piecewise given here is f of x is equal to the bracket x squared minus 1 when x is less than 2. An absolute value of x minus 2 when x is greater than 2. First thing I'm going to show you is how to evaluate the function, because that's going to help you realize what's going on here. So remember when we say f of 1, we are saying x is 1, what is the value of the function, our y? In the case of 1, that is less than 2. So that's going to be found on this graph right here, that x squared minus 1. And so 1 squared minus 1 is 0. F of negative 2 is also in this domain. Negative 2 is less than 2. So we would use this equation again. Negative 2 squared is 4. Minus 1 is 3. Remember, if you're putting that in the calculator, you've got to put that negative 2 in parentheses with the squared on the outside. 0 is also less than 2. And when I plug that in here, 0 squared minus 1 is negative 1. So for all of these equations, we use the x squared minus 1 because our x value was less than 2. On the 2 that we have down here, x is 3. 3 is greater than or equal to 2, so we're going to use this equation right here. So we would do the absolute value of 3 minus 2. 3 minus 2 is 1, and the absolute value of that is 1. If I plug in the 2 here, 2 minus 2 is 0, and the absolute value of 2 is 0. We are going to fill out a table now, just so you can see that. We used all of these equations with x minus 2. So for the x squared minus 1, that's one where x is less than 2. So I would start with 2. Now, since it is only less than, it is not equal to, that is going to be an open circle when I graph it, because there's not going to be a point at 2 since it is not equal to. And the numbers that are less than 2 are 1, 0, negative 1, and we'll stop there. For the second equation, it is talking about when x is greater than or equal to 2. So I would start with that 2. It does have an equal sign on that one, so that is going to be a closed circle. And the numbers that are bigger than 2 are 3, 4, 5, and so on. That'll give us a good view of what our graph looks like. When we look at 2, we had that value right here. Oh, sorry, that was on the first one. 2 on this first one, 2 squared is 4, minus 1 is 3. This is the 2 that we have here, the one that is equal to, and that would be 0. For 1, that we have right here, so that is 0. For 0, we have it right here, it is negative 1. For negative 1, we didn't have that one, so I'm going to plug it in here. Negative 1 squared is 1, minus 1 is 0. Now we move to our second equation here. The 3, we had it right here, it was 1. The 4 we did not have, so we plug into here. 4 minus 2 is 2. In the absolute values, it comes out as a positive always. Anything that comes out of the absolute value comes out as positive. 5 minus 2 is 3. The absolute value of 3 is 3. Now we're ready to graph this. I'm going to start graphing these first ones. So I go to 2, 3, and I'm going to do my open circle there because we decided it was open since there was no equal sign. Then I got a point at 1, 0, 0, -1, -1, 0. We actually still have this one here at -2, 3. If you wanted to graph more points so you could see what's going on. That's a quadratic. It's got that U shape. So I'm going to connect my points here. And I would stop at that open circle because that's where that domain restriction is. That's what these are called right here. Domain restriction. Now we're ready to graph the second one, and it starts at 2, 0. And that was a closed circle. So I'm going to start there with a closed circle. And then 3, 1, 4, 2, and 5, 3. And we get a vertical line here that looks like that. It was an absolute value, just doesn't have the other side of that V. All right, so some of the things we're going to have to think about with these piecewise is domain and range and continuous or discontinuous. If we look at this graph right here, all of these are continuous. I do not have to pick up my pencil until it gets to this point. I cannot continue graphing without picking up my pencil. It jumps down here. So this is discontinuous. If I have to pick up that pencil, it is discontinuous. There are 3 types of discontinuities. I'm just going to put those up here real quick so you can see those. Here it is. It tells us a continuous function is a function whose graph has no breaks. You can sketch the graph without picking up your pencil. There is a removable discontinuity. We talked about that in Algebra 2. That's when we referred to it as a hole. It is a point of discontinuity, is when a function is defined differently for only a single point. A removable discontinuity occurs when we simplify a term in the numerator and denominator, which indicates a hole in the graph. So that is when we only have one point on the graph that is discontinuous. A jump discontinuity is when the graph of the function seems to jump from one piece to the other. That's what we just saw there. It jumped from one graph to the other one and then continued. And the last one is an infinite discontinuity for asymptotic discontinuity. Occurs when a graph approaches infinity at a specific value. We saw that on rationals. They had the 2 pieces that never connected. So it jumped from one to the other because of the asymptote. So that's where you'll see an infinite discontinuity. The most popular one you're going to see in piecewise is the jump discontinuity. And that's what that one was. So I'll go ahead and label it over here. That was a jump discontinuity. All right, for our domain. Right here, we said we used this graph when x was less than 2, and we used this one when x was greater than or equal to 2. That includes all of the points. So our domain is from -infinity to infinity. It sees every point to the left and every point to the right. For our range, it starts right here and then goes up forever. Every y value above this one is represented. Yes, there's other ones over here, but you don't have to repeat them. So this would start at -1 and go up to infinity. All right, that was a lot, so we're going to try another one. Here we go. It says graph the following piecewise here and evaluate again. So we're going to go ahead and evaluate these by plugging in the x value into its corresponding equation. If you want, go ahead and pause and plug those in and then come back and check your work. All right, so the first row here, I evaluated by plugging those x values into the -x minus 3 because that's where those values were all less than or equal to 0. For the second one, I used the x squared plus 1 because those values were bigger than 0. And for 0, I used that first one because that's where it was equal to. We are going to go ahead and do a table of values again, and we'll start with the same process we did last time. So the first equation is when x is less than or equal to 0. So I start at 0 and I decide that's going to be a closed circle since it's got an equal sign. And then the values that come below 0 are -1, -2, -3, -4, and -5. I would then take these points and plug them into my function here to get their corresponding y values. For the x2, I start at 0 again because that's where this domain starts. That one does not have an equal sign, so I'm going to have an open circle on that one. And then I'm going to go to the numbers that are bigger than x. Now all we have to do is plug them in. Yes, you could put those into a calculator as well and use the table of values from that, but sometimes you don't have a calculator, so you should be able to plug them in. So here is your table of values. Go ahead and look at those. Make sure you got them all right. And now we'll start putting those on the graph. So we start at 0, -3, and that is going to be a closed circle. Then -1, -2, -2, -1, -3, 0, -4, 1, and -5, 2. And we go ahead and connect our dots. And so there is our graph. Now we go over to the other side and we've got 0, 1. That is an open circle, so I'm just going to make an open circle there. And then 1, 2, 2, 4, sorry, 2, 5. And 3, 10 goes above this graph. So I'm going to go ahead and stop there and just make the curve towards those points. Here is our new piecewise function. Again, this one is a discontinuous graph. And it has that jump discontinuity again. I can make this entire line with my pencil on it, then I have to jump to that next one. My domain here is from -infinity to infinity, since we have every single x value represented on this graph. And our range starts down here. There is a point there, so I'm going to make a bracket. And then it goes up forever, so this is going to be infinity. A lot of people want to stop that because there's an open circle here. But y is not right here at -1, but there is a y value of -1 right here, so it is somewhere on my graph. So that point has to be included. All right, you're probably thinking, can I put this in my calculator? Yes, you can. So I'm going to show you that. In order to put it in the calculator, you have to set it up kind of awkwardly. Whoops. So here is what it should look like. It kind of looks like a fraction, and in the numerator, you are going to put the equation, and in the denominator, you're going to put the domain restriction. I'm going to show you how to do that on the second one there. So we hit alpha y equals, gives you that numerator over denominator. Then I'm going to put in the x squared plus 1 in my numerator, and then I'm going to want to put my domain restriction in my denominator. So I hit x, and I want to say is greater than 0. In order to get the greater than sign, you have to hit second. I'll show it to you down here. Second, and then math to get to that test part. The test is going to give you the inequalities. Sorry about that. There's a glare on my calculator. Let's see if I can get that better. There we go. And I want it to be the greater than 0. So that's that number 3 there. And then 0. And then when I hit graph, it will go ahead and show my piecewise equation, which is exactly what we just drew. So you have to do that divided part just so that it restricts the domain. If you go to the table now, it also shows you the two tables for the values. So evaluating this is easy using the calculator. But again, you're going to have the calculator on some portions and not on others. So you want to make sure you're able to do it algebraically as well. All right, we are going to try a little bit more. In an effort to not make this video terribly long, I'm going to go ahead and just show you the next example. You can have 3 equations defined here, or 4 or more. So I wanted to show you one of those. The process is exactly the same. So on the table here, we did put all three equations. I did decide which one is going to be a closed circle and which ones are going to be open circles to keep that as a function. I've got another closed circle on that one right there. Remember, closed circle happens when there is an equal sign. So at -1, I want to do this one at a closed circle. At -1, I want to do this one with an open circle. And then I can graph all 3 points for those domain restrictions. So for less than or equal to -1, this graph has to stop at -1. The next one goes from -1 to 2, so from -1 to 2. And then the last one goes from 2 to infinity, so it goes to the right. So I did want to give you an opportunity to look at that when there is more than just 2 equations graphed there. That's okay. All right, the last thing we're going to do is write the equation from a graph. So if you've got a piecewise that you are given, then you should be able to write the equations at this point and work backwards to write this piecewise. In this case, we're going to break it down into pieces for you, but in most cases on a quiz or test, you would just be given this last part, write a piecewise function, and then the graph. Looking at this graph, if you know your parent functions, you know what these two graphs are. The one on the left is a quadratic because it's that U shape. And then the one on the right is a line. Some people could say that's an absolute value. That's true. It would just make it a little bit harder for you to write, so you might as well write the line one. As long as you get one that does work on that, though, it would be okay. I like to write the domain restrictions first because I can see this portion of the graph is my parabola and this portion of the graph is my line. So when x is less than 0, that's where I'm going to have that parabola. I have no line here for the equal sign because that is an open circle. The one on the right here, it has a closed circle. So when I say the domain restriction on that one, I will put a line there for the equal sign. X is greater than or equal to 0 because it goes to the right of that value. Now to write the equations. My vertex is at 0, 0, just like the parent function. So I know that it's not moved up or down or left or right. It goes to the right one and up one, and to the left, and to the left 2 and up 4. So I know there's no stretches or compressions or reflections. So that is just my parent function. For this right one, we write the equation of a line, if you remember, y equals mx plus b. B being the y-intercept, m being the slope. So my y-intercept is -5, and my slope is 2. I've gone up 2 and to the right one. So, oops. I don't have to write the y in this case because it's going into the piecewise thing. But usually when we write an equation, we have the y equals. So my slope there was 2, so I get 2x, and my y-intercept was -5, so it is -5 there. Now I'm ready to write my piecewise. It is x squared, comma, when x is less than 0. And then it is 2x minus 5, comma, when x is greater than or equal to 0. That's our piecewise functions.